Imagine walking into a busy office building with hundreds of devices and multiple Wi-Fi routers. For your IoT sensor to work reliably, it can't just connect blindly to the first network it sees. It needs to know which networks are available, which have the strongest signal, which require a password, and which channels are already crowded. This process is called network scanning, and on the ESP32 it's not a nice-to-have feature. It's the foundation for robust IoT connectivity. Without scanning, your device might attach to a weak or unstable access point, causing random dropouts and poor performance. With scanning, you empower your project to make smart choices, like always connecting to the closest AP or logging coverage for deployment planning. By the end of this lesson, you'll not only understand how scanning works but also how to interpret and apply the results in real-world projects. Think of Wi-Fi scanning like being in a train station. Every access point is broadcasting its announcement, and the ESP32 listens carefully as it sweeps across channels. Each beacon provides 4 critical pieces of information. First, the SSID, that's the network's name, the label you see when connecting on your phone. Second, the RSSI, or Received Signal Strength Indicator, which tells us how strong the signal is in dBm. Third, the encryption type, which reveals whether a password is required and what security standard is used. Finally, the channel, which indicates the specific frequency band the network operates on. Together, these details form a complete map of the wireless landscape. Once you learn to read this map, you can pick the best access point, troubleshoot coverage gaps, or even measure how dense a building's Wi-Fi environment really is. When the ESP32 performs a scan, it disconnects from any existing Wi-Fi to free up the radio hardware. Then, it systematically hops through available channels, listening for beacon frames from nearby access points. These beacons contain metadata such as SSID, signal strength, security type, and channel information. After collecting the results, the ESP32 makes the list available for your code to process, typically through the serial monitor. You'll see each detected network printed in rows, including SSID, RSSI, encryption, and channel. This structured output isn't just useful for deciding which network to connect to. It can also be logged for future analysis, used to trigger fallback decisions, or even combined with GPS for location mapping. In professional IoT deployments, network scanning becomes a key tool not just for connectivity but also for diagnostics and adaptive system design. Signal strength, measured as RSSI, is one of the most important scan results, but it confuses beginners because values are negative. Closer to 0 means a stronger connection. For example, -40 dBm is excellent, like standing next to the router. -70 dBm is usable but less stable, especially under load. Once you drop below -85 dBm, the connection becomes unreliable and packet loss is common. In field deployments, I often walk through a site with an ESP32 in scan mode, logging RSSI at different points. Why? Because the RSSI reported by the ESP32 is often weaker than what a laptop shows due to antenna differences. If your IoT device has to operate in the farthest corner of a building, you must design for worst-case RSSI values, not ideal conditions. Knowing how to read RSSI helps you plan reliable coverage and avoid frustrating dropouts. Not all Wi-Fi networks are equal when it comes to security. During a scan, the ESP32 tells you the encryption type for each network. Open networks, Wi-Fi_open, allow anyone to connect without a password, easy for testing, but highly insecure. WPA2 is the standard you'll see most often. It uses a pre-shared key, PSK, and provides good protection for IoT devices. WPA3 is newer and stronger, but some IoT hardware, including older ESP32 libraries, may not fully support it yet. Sometimes, routers run in mixed WPA to WPA3 mode to ensure compatibility. As a rule, always prefer WPA2 or WPA3 when building IoT systems. If your project must connect to an open network, you should add security at the application layer. For example, using TLS for MQTT communication. Recognizing encryption types isn't just academic. it directly impacts how safe and future-proof your deployment will be. Let's see scanning in action with an example sketch. First, the ESP32 disconnects from any connected network so the radio is fully available. Then, it runs Wi-Fi.scan networks, which sweeps through every Wi-Fi channel. For each detected network, it collects the SSID, SSI, encryption type, and channel. The code prints this information neatly into the serial monitor, so you can scroll through and see exactly what's nearby. You might find 5 or 10 networks around you, each with varying signal strengths and encryption. To test, you can even turn your phone's hotspot on and off and watch the ESP32 detected dynamically. This hands-on exercise helps confirm that your ESP32 is truly listening to the wireless environment and reporting accurate data. Practicing with this sketch is the first step toward building smarter, self-adjusting IoT devices. Raw scan results are just the beginning. The real value comes from using them to make smarter decisions. For example, your firmware could automatically connect to the network with the strongest RSSI instead of a fixed SSID. Or it could prefer networks that use WPA to WPA3 for stronger security. You can even implement fallback logic. If the primary AP is unavailable, connect to the next best one. In advanced projects, developers log scan data over time to detect signal fluctuations or interference patterns. This allows you to predict problems before they occur. Think of scan results as a constantly updated map. By teaching your IoT device to read that map, you transform it from a blind connector into an intelligent system that adapts to changing environments. This adaptability is what separates hobby projects from professional-grade IoT deployments. Wi-Fi scanning is powerful, but it comes with traps. First, don't scan too often. Each scan consumes a lot of power, which is especially harmful in battery-based projects. Instead, scan at intervals or only when necessary. Second, crowded areas like apartments may show dozens of overlapping SSIDs. Always pay attention to the channel values to avoid interference. Third, don't rely on a single scan. Wi-Fi is noisy, so average results over multiple scans for accuracy. Finally, never underestimate antennas. The built-in ESP32 antenna may work in small projects, but industrial deployments often need external antennas for stable performance. I've seen many mystery dropouts solved by simply improving antenna placement. Keeping these tips in mind will save hours of frustration and make your Wi-Fi scanning code production ready. Once you master scanning, the next step is applying it creatively. For example, in asset tracking systems, devices can scan Wi-Fi networks and use their SSIDs as location fingerprints. In smart building projects, scans can measure Wi-Fi density to help optimize router placement. In industrial IoT, scan data helps predict interference zones where machines might block signals. Even simple consumer devices, like smart speakers, use scanning to decide which access point gives the smoothest streaming. In my projects, I've even used scan data as part of a watchdog. If our SSI drops too low, the device triggers an alert. The point is, scanning isn't just about connecting, it's about turning wireless chaos into structured, actionable information. This shift in perspective opens up a whole range of advanced IoT designs where connectivity becomes smarter and more resilient. Let's recap what you've learned. The ESP32's Wi-Fi scanning feature is the foundation for building smarter, more reliable IoT devices. You now know how scanning works, what details are collected, SSID, RSSI, encryption, and channel, and how to interpret them in real-world conditions. You've practiced reading RSSI values, recognized encryption types like WPA2 and WPA3, and seen how to run a basic scanner sketch. More importantly, you've learned how to avoid common pitfalls like excessive scanning or ignoring antenna design. By applying scan results thoughtfully, your IoT device can adapt to the best available network, troubleshoot weak coverage, or even log Wi-Fi density for planning. With these skills, you're ready to move beyond trial-and-error connectivity and design systems that make intelligent network choices on their own. This is a major step toward building professional-grade IoT solutions.